basic sheet on Ellipse. Ellipse, just the basics, which is direct application of results that we covered in the last class. I'm assuming you would have attempted some problems by this time. Let's make sure that we've done it all right. All right. So this sheet titled Ellipse, just the basics. The first problem is about a curve x squared by 10 minus a plus y squared by 4 minus a equal to 1. We want to be able to find the values of a, range of a, for which this could represent an ellipse. Now compare it with the standard form of the equation of an ellipse, x square by a square plus y squared by b squared equal to 1. Very clearly this is greater than 0, this is also greater than 0. Consequently 10 minus a must be greater than 0, 4 minus a must be greater than 0. So 10 minus a greater than 0, which means a less than 10, right? And along with this 4 minus a must also be greater than 0, which would mean a less than 4. Now if I combine these two, the combination of these two is like a less than 4, a less than 4. So the range of a is a belongs to minus infinity to 4. If a belongs to minus infinity to 4, this is capable of representing an ellipse. Yes or no? Has three subparts A, B and C. The second problem, part A, is about trying to find the equation of an ellipse whose foci are 2, 3 and minus 2, 3. These are the two foci S and S prime, and whose semi-minor axis B is root 5. Semi-minor axis B is root 5. That's given, right? Now, one thing, even though we studied ellipse in this standard form, x square by a square plus y square by b squared equal to 1, this ellipse had center given by x square equal to 0 and y square equal to 0. That means 0, 0 was the center of this ellipse. The origin was the center of this ellipse, right? And if a was greater than b, then this ellipse looked like this. If a was greater than b, its major axis was lying along the x-axis if a was greater than b. If a were to be less than b, things will just flip. They will look like this. If a was less than b, then the major axis would lie along the y-axis. That means b, right? Would be the major axis. If, in contrast, the ellipse didn't have center 0, 0, and axis, major and minor axis, let's say A and B, semi-major, semi-minor axis, but had center h comma k. If an ellipse had center h comma k, not the origin, then something like this, x minus h whole squared by a squared plus y minus k whole squared by b squared equal to 1 was an ellipse with center h comma k. Now if a was more than b, then the ellipse would look like this. If a was more than b, this would be an ellipse in which a is more than b. Its major axis is parallel to the x-axis. Major axis is parallel to the x-axis. Its minor axis is parallel to the y-axis, right? Provided a was more than b. The same ellipse, if a was less than b, but center h comma k would be like this. This is a less than b, and center of this ellipse is h comma k. H comma k would be the center of this ellipse, right? So the orientation will depend on whether a is less than b or a is more than b, right? Now one important thing is, if the center of the ellipse was the origin of coordinates, which is the case here, please mark this. If the center of the ellipse was the origin of coordinates, which is the case here, right? There is no presence of x term in this equation. There is no presence of xy term. The coefficient of x is 0 here. Coefficient of, I'm sorry, this is equal to 1, not 0. This is equal to 1. Coefficient of x is 0. Coefficient of xy is 0. Coefficient of y is 0. Right? That was an ellipse. Whose origin was whose center was the origin of coordinates. This is an ellipse whose center is not the origin, but is center h comma k. This form of the equation of an ellipse will look something like this: ax squared, if you collect terms, plus by squared plus 2g into x plus 2f into y plus c equal to 0. If you cross multiply collect terms, this would be the formation of such an ellipse. Yes or no? Do you realize this will have an x term, this will have a y term, but the coefficient of xy will be 0 in this. So if in the generalized equation of second degree in x and y, if the curve represents an ellipse, whose axes are parallel to the x and y axis, that means parallel to the coordinate axis, center is not the origin, however, then the x and y terms will appear, but the xy term will be 0. Coefficient of xy will be 0, right? And one in which the coordinate axes themselves act as the major and minor axis, and the center is the origin of coordinates. Neither the x term is there, nor the xy term is there, nor the y term is there, right? And in an ellipse in general, if there was an ellipse whose axes, major and minor, were not parallel to the coordinate axis, then that would be the generalized ellipse that will have coefficient of x non-zero, coefficient of y in general non-zero, coefficient of xy in general non-zero. Do you all understand this? Right? And one thing very important is that the minor axis will always be parallel to the directrices. The minor axis will always be parallel to the directrices. The major axis will be perpendicular to the directrix. And the midpoint of the line joining the two foci would be the center of the ellipse. The midpoint of the line joining the two foci would be the center of the two ellipse. Yes or no? Right? Now, coming to this problem. So these are facts, simple observations. Now, if this is an ellipse, realize that this is the major axis. And this is a line parallel to the y-axis. This is a line y equal to 3. This is a line y equal to 3. Right? Its major axis is parallel to the y-axis, is parallel to the x-axis, and its minor axis will be parallel to the y-axis. Such is this ellipse, right? The center of this ellipse will no longer be the origin of coordinates, but would be the midpoint of these two. So the midpoint of these two would be 0, 3 would be the midpoint of these two, right? So I know the center of this ellipse, right? Now, this ellipse would have b equal to root 5. Realize the difference between the two foci. The separation between the two foci is 2ae. 2ae is the separation between the two foci, right? And that's very clearly equal to 4 units. Let me call this minus 2. Let me call this 2. That's going to be 4 units. That's going to be 4 units. That means AE is 2 units. Yes or no? Now, very clearly, E is root 1 minus B square by A squared. That's equal to 2. Isn't it? I want to find A, the semi-major axis. I know B, right? This is like root A squared minus B squared is 2. Or A squared minus B squared is 4. Or A squared would be 9. A would be 3 units. A would be 3 units. Right? So now I have an ellipse whose semi-minor axis is root 5, semi-major axis is A equal to 3, and whose center is 0, 3. Would you not want to believe the equation of this ellipse would be x minus 0 whole squared by A squared plus y minus 3 whole squared by B squared equal to 1. It will have no xy term in it. It will have no xy term in it. Yes or no? We want to find the lengths of the major and minor axes, the coordinates of the foci, vertices, and the eccentricity of the ellipse. We have an ellipse which is like 3x squared plus 2y squared equal to 6. That's the ellipse. That's the ellipse. Now this ellipse could be written as x squared by 2 plus y squared by 3 equal to 1. Realize that b square is more than a square, right? Right? So the y-axis will serve as the major axis. The y-axis will serve as the major axis for such an ellipse. Yes or no? And obviously the center of the ellipse is the origin of coordinates, right? So this ellipse will look like this. The origin is the center, right? A is root 2. A squared is 2, so A is root 2. B is root 3. B squared is 3. B is root 3, right? The eccentricity of this ellipse, E squared, is 1 minus B, in this case, 2 by 3, right? In this case, 2 by 3, the smaller by larger, right? 1 minus 2 by 3, which is 1/3. The eccentricity therefore is 1 by root 3, right? Then one focus, which is this, will be 0 comma BE. 0 comma BE would be one focus, which is like 0 comma B is root 3 plus 1. 0 comma plus 1, and if this is 0 comma plus 1, this is the origin which is also the center, then the other focus S prime, because of symmetry, is going to be 0 comma minus 1 would be the other focus. Yes or no? Right? There are 4 vertices. Very clearly, this is 0 comma root 3. This will be 0 comma minus root 3. This would be root 2 comma 0, right? A is root 2. This is minus root 2 comma 0. What else do we need to find? We have found the foci, vertices, and eccentricity of the ellipse. The major and minor axis, the lengths of the major axis. The major axis would be 2b. Major axis would be 2b in this case. 2 root 3. The minor axis would be of length 2a, 2 root 2 in this case. Yes or no? These would be the major and minor axis of this. Clear? No issues with part 1. 2c part 1. We want to find the equation of an ellipse with the following specification. 1. The center of this ellipse is 1 comma 2. And one of the foci is 6 comma 2. That means the line joining the center and the foci will lie along the major axis. That means the major axis is very clearly y equal to 2. Y equal to 2 is the major axis, isn't it? It's an ellipse whose major axis is parallel to the x-axis, right? Y equal to 2. And passing, there is a certain point on the ellipse P, which is 4 comma 6 is a point on the ellipse. We want to find the equation of such an ellipse. Clear? Okay. Very clearly, this is center C, 1 comma 2. This is one focus S, 6 comma 2, right? Then this would be the other focus S prime. This would be the other focus S prime. Very clearly, it's, sorry, how much? Minus 4 comma 2, right? Minus 4 comma 2. Y would be the same, and C is the midpoint. So 6 minus 4, 2 by 2, 1, which will give me the center, right? So since C is the center of the line joining S and S prime, the other focus should be minus 4 comma 2. This is obviously the line Y equal to 2, right? There is a point P on the ellipse which is 4 comma 6. 4 comma 6 is a point on the ellipse. Now SP plus S prime P would be the major axis 2A, right? Will be the major, so I can find small a of the ellipse, right? Small, very clearly the form of this ellipse would be x minus 1 whole squared by a square, square of the semi-major axis, plus y minus 2 whole squared by b square, square of the semi-minor axis, equal to 1, right? I can find a from these considerations. So how much is this? This is SP, which is 100, so that is 10 S prime P. 4 plus 16, isn't it? 10 plus 2 root 5, is it? Or have I made a mistake? SP, which is 864 plus 16, 80, root 80, right? Root 80 plus root 20, isn't it? Which is 4 root 5 plus 2 root 5, which is 6 root 5. Is 2A, is 2A, isn't it? This is 2A, SP plus SP prime is 2A. So A then is 3 root 5, A is through, isn't it? S prime P plus SP, distance formula. I get that as 2A. So A is 3 root 5, A is 3 root 5. Now the distance between the two foci is 2AE. 2AE is the distance between the two foci. And this distance is 10 units. This distance you can see is 10 units. And E then would be 10 divided by 2A, that is 6 root 5. So I know the eccentricity of this ellipse, right? I can find B square. 1 is A squared into 1 minus E squared. I can find B square from these considerations. I know A, I know E. So I can plug in the value of B here. I can plug in the value of A here. And there I have the equation of the ellipse. Yes or no? We want to find the equation of an ellipse with a focus S. One of the foci is minus 1 comma 1. The eccentricity of this ellipse is half, and the directrix of this ellipse is x minus y plus 3 equal to 0. Very simple. See, if this is the directrix, x minus y plus 3 equal to 0. This is the axis of the ellipse. And if S be a focus, in this case minus 1 comma 1, and P be any point on the ellipse x comma y, and the perpendicular distance of P from the directrix is PM, and this is SP, then by definition, if P is any point on this ellipse, SP squared would be E squared times PM squared. SP squared would be E squared times PM squared. SP squared means this square of this distance, x plus 1 whole squared plus y minus 1 whole squared is e square. E square would be 1 by 4 into pm squared, square of the distance of xy from this line, which is x minus y plus 3 divided by root 2 whole square. Square of the distance of P from the directrix is this perpendicular distance. Right? Now you can cross multiply. Now this will have everything in place. It will have an x square term, a y square term, an xy term, and an x term, and a y term, everything. So in a general sense, it's an ellipse whose axes are neither parallel to the x-axis nor parallel to the y-axis, not parallel to the coordinate. This is an ellipse whose axis is an oblique axis, Clear? Is about a curve 10x minus 5 whole squared plus 10y minus 5 whole square equal to 3x plus 4y minus 1 whole square. We want to establish that this represents an ellipse, and we want to find the eccentricity of that ellipse. Okay. Now what I do is I take 10 common from this. When it comes out, it will become 100. Same thing I do here, right? So 100 into x minus half whole squared plus y minus half whole squared equal to, now 3x plus 4y minus 1 equal to 0 is like a straight line, and distance of xy from this straight line is going to be given by 3x plus 4y minus 1 by 5 whole square, and I balance it so that this essentially represents distance of a point xy from a line 3x plus 4y minus 1 equal to 0. Yes or no? Right? And this 100 then I transfer here 1 by 4. Now what does this mean? It's as if there is a point half comma half. There is a point half comma half. And there is a moving point px comma y, and there is a line 3x plus 4y minus 1 equal to 0. There is a line 3x plus 4y minus 1 equal to 0, and the left hand side represents sp squared, isn't it? The left hand side, square of the distance of s from p. The right hand side is square of the distance of p from this line. So the left hand side is sp squared, isn't it? The left hand side is sp squared. Now the right hand side is 1/4 half whole square into pm squared, isn't it? Very clearly p moves in a manner that square of its distance from s is e square times square of its distance from the directrix. That means the locus of p must be an ellipse whose directrix is this, whose focus is this, and e squared is half squared, e must be half, the eccentricity must be half of such an ellipse. Yes or no? The eccentricity of this ellipse is half. This, I took 10 common, so there was 100 here. Right? Right? And this I divided by 5 means actually 25, and I placed a 25 here. And then this came here, so that was 1/4. Now all that I am doing is interpreting this result. This is a moving point x comma y. Square of the distance from half comma half, this is sp squared, is 1/4 into square of the distance of xy from a line 3x plus 4y minus 1 equal to 0. right? So it's like SP squared is E squared into PM squared. On comparison, this must be an ellipse with focus half comma half, with directrix 3x plus 4y minus 1 equal to 0, with E squared equal to 1 by 4, so equal to half. Yes, please ask a question. Okay, but this is all right, right? We have an ellipse, and this is the focus of the ellipse. This is the focus of the ellipse, right? This is the focus of the ellipse, which is, let me say the ellipse is x square by a square for definiteness, x square by a squared plus y square by b squared equal to 1, right? Now, this is a focal chord AB. This is a focal chord AB. How many focal chords can be there? Infinite focal chords. Every time you draw a focal chord AB, you can draw tangents at the extremities of the focal chord. You can draw tangents at the extremities of the focal chord, and these tangents intersect at the point P. These tangents intersect at the point P. Now, for different focal chords AB, I'll have different positions of P. So if I keep drawing various focal chords, I end up getting various P's. I now want to show that the locus of these P's is the directrix of the ellipse. That means no matter where P lies, its x coordinate would be A by E. Its x coordinate would be A by E. This is what we want to establish. If the x coordinate of P for any AB is A by E, then the locus of P is the directrix. Yes or no? You know what exactly to establish? Suppose for a certain AB, P has coordinates h comma k. Now, can I look upon AB as a chord of contact with respect to the point P? So the equation of AB is t equal to 0. Equation of the chord of contact with respect to P is going to be t equal to 0. So if I look upon AB as a chord of contact with respect to P, h comma k, then the equation, that is AB, its equation is going to be t equal to 0, which is like hx by a squared plus ky by b squared equal to 1. Yes or no? So that's the equation of the focal chord AB. But if it's a focal chord, should it not pass through AE comma 0? If it's a focal chord, should it not pass through AE comma 0? That means this equation is satisfied no matter what P. This will always be a focal chord and it will always pass through AE comma 0. So you can plug in x equal to AE and y equal to 0. That will be satisfied. So plug in x equal to AE. So you have h by a squared, x equal to AE, and y equal to 0 will give me 1. X equal to AE, y equal to 0 will give me h by a squared. AE is equal to 1, yes or no? So this gives me the x coordinate of the point P. H is A by E. That means for all P's, the P's will always have their x coordinate equal to A by E. That means the locus of P is like the line x equal to A by E, which is necessarily the directrix. Which is necessarily the directrix of the ellipse. Yes or no? Right? So this is a result you might even want to remember. Tangents drawn at the extremities of a focal chord will always intersect on the directrix. Tangents drawn at the extremities of a focal chord will always intersect on the directrix. Right? And if various focal chords are drawn, then the points of intersection of these tangents will constitute the directrix of the ellipse. An important result, you might want to keep a note of it, right? Now the fifth problem. The fifth problem is about an ellipse. Let me refer to this ellipse as a standard ellipse. X squared by a squared plus y squared by b squared equal to 1, right? Now, the locus of the point of intersection of tangents to an ellipse at 2 points whose eccentric angles differ by a constant angle alpha. Now, what I do is, I select 2 points P, say theta 1, and Q, say theta 2, where say theta 1 minus theta 2 is alpha. Obviously, several sets of PQs could be selected where they differ in their eccentric angles by alpha, right? Every time you select PQ such that difference in their eccentric angles is alpha, and you draw tangents at these points, and you draw tangents at these points, these tangents intersect at a point M. These tangents intersect at a point M. We want to find the locus of M. We want to find the locus of all such M's, right? Now, if M has coordinates h comma k, then if you recall a result that we discussed in our concept class, h is x coordinate of M is going to be a cos theta 1 plus theta 2 by 2 by cos theta 1 minus theta 2 by 2, right? Yes or no? But theta 1 minus theta 2 is alpha, so this will become a cos theta 1 plus theta 2 by 2 by cos alpha by 2. That's h. K is b sine theta 1 plus theta 2 by 2 cos theta 1 minus theta 2 by 2, right? Which is like b sine theta 1 plus theta 2 by 2 by cos alpha by 2. I need to eliminate theta 1 and theta 2, which are my parameters. Very clearly, from this equation, I can find cos theta 1 plus theta 2 by 2. So, h cos alpha by 2, h cos alpha by 2 by a whole squared. See, h cos alpha by 2 by a whole squared is cos square this plus k cos alpha by 2 by b whole squared would be sine square this. Cos square theta plus theta 1 plus theta 2 by 2 plus sine square theta 1 plus theta by 2 is 1. Yes or no? And then you generalize, replace h by x and k by y to get the locus of M. H by x and k by y to get the locus of M. Eliminating the parameters theta 1 and theta 2. This is the locus of M, intersection point of the two tangents thus. Yes or no? Right? No confusion? Now, number 6. A point moves so that the sum of squares of its distances from two intersecting non-perpendicular straight lines. Two fixed straight lines are given that are not perpendicular to each other, right? And they intersect. That means they are not parallel either. They are non-perpendicular, non-parallel straight lines. And sum of the squares of this distance from these two fixed points, fixed lines, is a constant. We want to show that the locus of such a point is an ellipse. Locus of such a point is an ellipse. So I have essentially a straight line like this, and a straight line like this. These are two lines. They intersect and they are not perpendicular to each other. Okay. And there is a moving point P. There is a moving point P such that its distance from this PA squared plus PB squared is a constant. This point P moves in a manner that PA squared plus PB squared is a constant. Is a constant C. We want to establish then that the locus of P is an ellipse. Locus of P is an ellipse. See, when they don't predefine the coordinate axis and the origin, then you had the luxury of defining your own origin of coordinates, your own x-axis and y-axis therefore. And one thing, the physicality of a situation will not depend on choice of coordinate axis. An entity which looks like a circle in one set of axes will still look like a circle in another kind of axis. So that fact will remain unaltered. All physicalities. If the eccentricity of an ellipse computed in one reference coordinates is half, it will be half in any reference coordinates. That's not good. Its major axis will be the same. Its minor axis. However, the formation of its directrices, in the sense, there will be the same lines, but the equation of the lines may change. But it's going to be the same set of directrices, the same set of foci. Physicalities do not depend on choice of coordinate axis. In this case, the physicality is that the point P describes an ellipse. Now exploit a situation where they have not defined the origin and they have not defined the coordinate axis. Where is the foci? I don't have the two foci here at all. I have nothing except these two lines and a moving point. Everything else is virgin here. Huh? No, these are moving points. If P moves, A and B are moving points. How can you look upon them as O? So one thing, yes, I would choose to call this an origin O. Not the center of the ellipse, origin of coordinates. Origin of coordinates. Again, what I want to do is, and you will see rationale. Although there is no hard and fast rule of doing this only. There is nothing cardinal about what I'm saying. You can have your own choice. But my contention here is, I want my x-axis to be such that it does not distinguish too much between the two lines. What I do is, my x-axis I can choose as the angle bisector between the two lines. The angle bisector between the two lines, I choose as my x-axis. The angle bisector between the two lines I choose as my x-axis. Now if the slope of this is tan theta, the slope of this would be minus tan theta. So if the slope of this line is m, the slope of this line will be minus m. Yes or no? So the equation of this line is like y minus mx equal to 0. Y equal to mx. And the equation of this passes, since it passes through the origin, right? The equation of this line is y plus mx equal to 0. That is y equal to minus mx. Y equal to minus mx. Yes or no? M and minus n are the slopes of the two lines passing through the origin. Yes or no? Is there any loss of generality in doing this? No loss of generality. Now, if P, moving point at a certain instant, has coordinates h, comma, k, right? then PS square, for example, will be square of the distance of HK from this line, which is K minus MH whole square divided by 1 plus M square, square of the distance of this line from P, isn't it? What? Square of the distance of this point from this line? K plus MH. I hope you haven't forgotten all these results. And that's equal to C? Yes or no? By this choice of x-axis, I've only simplified the algebra. Not that I've tinkered with the physicality of the situation, but I've simplified the algebra here. Because, see, this will be like same denominator now to deal with, k square plus k square, 2k squared by 1 plus m squared. Middle term gets cancelled. Then m square h squared, 2m squared h squared by 1 plus m squared equal to C? Yes or no? Can you write, replace h by x and k by y to generalize matters? Replace h by x and k by y to generalize matters? So would I not have x squared divided by c into 1 plus m squared by 2m squared plus y squared by c into 1 plus m squared by 2 equal to 1? C obviously has to be a positive constant because these are positive numbers. So C, so this is x square by a square plus y square by b square equal to 1, which is an ellipse, Now I would want you to ponder over this fact, which means in an ellipse, taking clue from this, in an ellipse, that means you will be able to find a pair of lines such that the sum of the squares of the distance of any point from the ellipse is a constant. For every ellipse, that means you can find such a pair of lines. And this is an ellipse with center 0, 0. That means this is an ellipse whose center coincides with the point of intersection of the two lines. Right? Which means even for a regular ellipse, x square by a square plus y square by b square equal to 1, can you then find those two lines such that sum of the squares of the distances from the two lines of any point in the ellipse is a constant? And what is that constant? Work on that. Right? You know what I'm saying? What is that constant C and what is that slope M? What are the two lines for any given ellipse then? That means which is the inverse of this problem? Right? Which is really the inverse of this problem. Given an ellipse, what are these two lines then? Problem number 7. We want to find the locus of the midpoints of focal chords of the ellipse. This is an ellipse. This is a focal chord. Different focal chords AB would have different midpoints M, H, K. M is the midpoint of a given focal chord, H, K. And different focal chords will have different M's. So if I keep changing my focal chords, this M would be a moving point? The midpoint of the focal chords would be a moving point? Yes or no? I want to be able to find the locus of the midpoint M. I want to be able to find the locus of the midpoint M of all focal chords. Yes or no? Simple. Can I write the equation of AB in terms of the midpoint M? T equal to S1. T equal to S1. So equation of AB in terms of the midpoint. Midpoint M is T equal to S1. Is T equal to S1, isn't it? Which is like hx by a squared plus ky by b squared minus 1 is the expression for T. S1 is h squared by a squared plus k square by b square minus 1. Minus 1 obviously will get cancelled. This is T equal to S1, equation of AB in terms of its midpoint M. But AE comma 0, no matter what chord I select, this line will always pass through AE comma 0. So put x equal to AE and y equal to 0. Put x equal to AE and y equal to 0. So this always passes through S. S, the focus. So put x equal to AE and y equal to 0. Y equal to 0. This would be, and then generalize that. Replace h by x and k by y to get the locus of M. Would you not want to generalize this now? Replacing h by x and k by y, right? That's the locus of M. And independently check and tell me sometime, what does this represent? What's the nature of this curve? Whether it's an ellipse or not an ellipse. All right. There is an ellipse which is x squared by a squared plus y squared by b squared equal to 1. There is an ellipse like this. And its foci are f1 and f2. f1 is one focus, AE 0, and f2 is another focus, minus AE 0. And P be a moving point on the ellipse, and P f1 f2 is a triangle. P f1 f2 is a triangle. We want to find the maximum possible area of the triangle P f1 f2. We want to find the maximum possible area of triangle P f1 f2. Now, suppose theta is the eccentric angle of P, then theta is my parameter. Any point P can be written as A cos theta, B sin theta. Any point on the ellipse can be written as A cos theta, B sin theta. Right? Now, this height would be B sin theta, isn't it? The y coordinate of P would be B sin theta. This would be B sin theta. The base is 2AE. The base is 2AE, distance between the two foci. So the area of this triangle, would be half of base, which is 2AE, into altitude, which is B sin theta. Which is ABE into sin theta. AB and E are fixed numbers. This will be maximum when sin theta is 1, right? Delta will be delta max when sine theta is 1, that means theta is pi by 2. Theta equal to pi by 2 is end of minor axis, right? So delta max is given by AB. E I can write as root 1 minus b square by a squared into maximum value of sine theta, which is 1, which is b root a square minus b square. B root a square minus b squared is the maximum when the point P either coincides with one end or the other end of the minor axis, 0 comma b or 0 comma minus b. Yes or no? Now there is an ellipse like this, x square by a square plus y square by b square equal to 1. X square by a square plus y square by b square equal to 1. And say this is a tangent drawn at a certain point P, say theta. That means this tangent is x by a cos theta plus y by b sin theta equal to 1. That's the equation of the tangent drawn at an eccentric angle theta. Now, f1 and f2 are the two foci. Then show that pf1 minus pf2, it should not be e1, we want to show, and if d is the distance from the center to the ellipse, from the center to the tangent, this CQ is D. CQ is D. It's given that CQ is D. The perpendicular distance from the center 0, 0 to the ellipse is D. CQ is D. Right? We want to show, we want to be able to establish that PF1 minus PF2 whole squared is 4a squared into 1 minus b squared by d squared. Pf1 minus Pf2 whole squared is 4a squared into 1 minus b squared by d squared. This is what we want to establish. Hey, this focus is say AE0. This then would be minus AE0, isn't it? Now what's the left hand side? Distance of the two foci from any given point is a plus ex and a minus ex. X of P, P has coordinates a cos theta, b sin theta. Then Pf2 is going to be a minus e cos theta, a minus ex, isn't it? And ae cos theta, right? And Pf1 is a plus ae cos theta. Yes or no? Have I given you this result? Distance of a point from the two foci a plus ex and a minus ex? Don't remember. If x, y are the coordinates of this point, then F2P would be a plus ex, a minus ex, and this is going to be a plus ex. I have not given this result? It's not possible because that's how I establish Pf1 plus Pf2 is 2a. Not distance formula, yaar. obviously not the distance formula. You guys don't even come ready with your notes. That's how I established that PF1 plus PF2 is 2A. I have obviously established this result. Yes, so A minus EX and A plus EX. Without this result, I wouldn't have established PF1 plus PF2 is 2A. So A minus EX and A plus EX. X is A cos theta for the point P. Now PF2 minus PF1 whole squared. If I take the difference, then I get A squared D squared cos squared theta. A squared D squared 2A squared 4A squared D squared cos squared theta. 4A squared D squared cos squared theta. Right? This difference squared is 4A squared E squared cos squared theta. Right? Isn't it? Now, I want to show that this is also 4A squared D squared cos squared theta. I want to establish this. Right? No issues so far, right? So, henceforth, don't forget the distance of a point from the focus. One focus is going to be A minus EX. The other focus is going to be A plus EX. X for the point P is going to be A cos theta with eccentric angle theta. Right? Now, look at the right hand side. 4A squared into 1 minus B squared by D squared. Look at this right hand side. 4A squared into 1 minus B squared by D squared. Can I find the distance D of 0, 0 from this line? Right? How do I find the distance D? D is distance of 0, 0 from this line. Put x equal to 0, y equal to 0 here. Right? Normal distance formula. Perpendicular distance of a point from a line. Root cos square theta by A squared plus sine square theta by B squared. Yes or no? 1 by D squared. See, we need 1 by D squared. So 1 by D squared then is cos square theta by A squared plus sine square theta by B squared. B square by D squared, so let me multiply by B squared because I need a B square by D squared. This is what happens. Yes or no? Then 1 minus this. So what I do is, first of all, I multiply with a minus sign. And then I add 1 to both sides. Multiplied with a minus sign and added 1 to both sides. And 1 minus sine square theta is going to be cos square theta. 1 minus sine square theta is going to be cos square theta. So this is like cos square theta minus B squared by A squared cos square theta. Now I need 4A squared into this. So 4A squared into 1 minus B squared by D squared. And that's simply going to be 4A squared into 1 minus B squared by A squared cos square theta. Right? Multiplying both sides by 4A squared and taking cos square theta common from these two. But what is 1 minus B squared by A squared? E squared. 1 minus B squared by A squared is E squared. So which is like 4A squared E squared cos square theta. Only algebraic simplification required in this problem. This is how it goes through. Yes or no? Which is the same as PF1 minus PF2 whole squared. 4A squared E squared cos square theta. Stand by. There are two ellipses. One is x square plus 4y squared equal to 4. The other one is x squared plus 2y squared equal to 6. These are two ellipses. Let me first rewrite them in standard form. This one, for example, x squared by 4 plus y squared by 1 equal to 1 is one ellipse, right? This ellipse, x squared by 6 plus y squared by 3 equal to 1. Obviously, the major axis of this is more than the major axis of this. The minor axis of this is more than the minor axis of this, right? They have a common center, 0, 0. So this ellipse would be on the outside, this ellipse would be on the inside, right? This is ellipse 2, let me call it E2. This is ellipse 1, let me call it E1. E1 would be inside, E2 would be outside, as you can see. They have a common center C. They have a common center C. This would be outside E2. This would be inside E1, which is this ellipse. Now, what we do is, a tangent is drawn to the inner ellipse. How many tangents could be drawn? Infinite tangents, right? So one instance of a tangent drawn to the inner ellipse, say, is this. This is a tangent drawn to the inner ellipse, right? This is a tangent drawn at a certain point, A, to the inner ellipse, E1. And this tangent would intersect the outer ellipse at P and Q. For different A's, you will have different pairs PQ. If I draw tangents at different A's, you will have different PQs, right? For every A, there is a PQ, and every time you get a PQ, you draw tangents at P and Q respectively. You draw tangents at P and Q respectively. These tangents intersect at a point M. These tangents at P and Q intersect at M. For different A's, therefore, you will get different M's. Different A's, you will get different M's. You want to show that the tangents, you want to show that PM will always be perpendicular to MQ. These tangents will be mutually perpendicular. We want to show that the tangent PM and the tangent MQ, no matter where I select my A, they will always be at right angles. This is what we want to show. Essentially, what do you want to show? You want to establish that M lies on the director circle of E2. You want to show that M lies on the director circle of E2. Have I done director circle in my last class? Right? Director circle of E2, the director circle of E2 is x square plus y square is a square plus b square. That means 6 plus 3, which is 9. That's the director circle of E2. That means if you select any point on the director circle of E2 and draw tangents to E2, then those tangents will always be perpendicular. That means if the coordinates of M are h and k, and if h square plus k square is 9, if h square plus k square is 9, then M will lie on the director circle. And if M lies on the director circle, the two tangents will be at right angles. So all that we need to show is h square plus k square is 9. Yes or no? Clear? Now, say A has coordinates x1, y1. Say A has coordinates x1, y1. On the inner ellipse, tangent is drawn at x1, y1, which is moving, right? PQ is a tangent at x1, y1, right? Now, you can look upon PQ as a tangent if I look upon PQ number 1 as a tangent at A x1 y1, then equation of the tangent A at x1 y1 is going to be x1 by 4 plus y1 by 1 equal to 1 would be the equation of the tangent at x1 y1. So PQ when perceived as a tangent at x1 y1 is going to be x1 by 4 plus y1 by equal to 1. Yes or no? 2. Look at this point M. For the outer ellipse, PQ is a chord of contact with respect to M. For the outer ellipse, PQ is a chord of contact with respect to M. So PQ now perceived as a chord of contact with respect to M. And the equation of the chord of contact with respect to M is going to be T equal to 0. Now for the outer ellipse, this is the outer ellipse, right? So I have hx by 6 plus ky by 3 equal to 1 is the equation of the chord of contact with respect to hk of this outer ellipse E2, of this outer ellipse E2, isn't it? Hx by 6 plus ky by 3 equal to 1. Now this and this both represent the same line PQ. And since one of their coefficients is equal, the constant term, all other coefficients must be equal. If one coefficient is equal, then both the other coefficients must also be equal. That means the equating coefficient of x here. So x1 by 4 must be equal to h by 6. And y1 by 1 must be equal to y by 3 equal to k by 3. Yes or no? Right? So x1 then becomes, as you can see, 2h by 3. y1 of course is k by 3, but x1 y1 is a point on the inner ellipse. So x1 squared by 4 plus y1 squared by 1 must be 1. Right? That's how I can eliminate x1 y1 and bring hk into light. Yes or no? So x1 squared by 4 plus y1 squared by 1 must be 1 because x1 y1 belongs to ellipse E1, satisfying the equation. Now x1 squared by 4 would be h squared by 9. x1 squared by 4 would be h squared by 9, as you can see. y1 squared would be k squared by 9. See, y1 squared by 1 would be k squared by 9 equal to 1. H square plus k square equal to 9, as you can see. That means hk lies on the director circle. Hk satisfies the equation of the director circle. That means if hk is the director circle of E2, the tangents drawn from hk to E2 will always be orthogonal or at right angles perpendicular to each other. Yes or no? Are you sure about this? Let's examine the next problem. 11. There is a curve given which is 4x squared plus a squared y squared equal to 4a squared, where a squared is greater than 4 and less than 8. A squared is greater than 4 but less than 8. We want to find a point on this curve. We want to find a point on this curve which is farthest from the point 0 comma minus 2. We want to find a point on this curve which is farthest from the point 0 comma minus 2. Farthest from the point 0 comma minus 2. You know what I'm saying? First of all, I can rewrite this as x squared by a squared plus y squared by 4 equal to 1, which is an ellipse. Which is an ellipse? A square greater than 4. A square greater than 4 means A must be the semi-major axis. Right? So here's my ellipse. A0 minus A0. No. 0, 2 and 0 comma minus 2 are ends of the minor axis, right? So this point 0 comma minus 2 is actually this point P. This is Q 0 comma 2. I want to find a point on this curve. I want to find a point on this curve which is farthest from P, which is farthest from P. Now, let me first solve the problem without computation. Let me first solve the problem without computation. Okay. Let me share one thing which about time I could share with you. Forget this problem for a moment. Forget this problem for a moment. Okay. This is any curve. Say y equal to fx. This is any curve, say y equal to fx. There is a point P, say x1, y1. There is a point P, say x1, y1, somewhere. I now want to be able to find a point M on this curve. I want to be able to find a point M on this curve such that distance between P and M is either the smallest or the largest. Distance between P and M is either the smallest or the largest. You know what I'm saying? The problem that I'm trying to address is, given a fixed point P x1, y1 and a curve y equal to fx, I want to be able to locate a point M on the curve such that Pm is the smallest it could be. Pm is the smallest it could be. You know what I'm saying? So far so good, right? Now, look at Pm squared's distance formula. And whatever I say now would come in handy not just for this problem, but let's say a family of problems. So take this as something very cardinal. Pm squared is x minus x1 whole squared plus y minus y1 whole squared. X minus x1 whole squared plus y minus y1 whole squared. This is a function of x and y. It's a function of x because y also is a function of x, right? Now, this Pm squared would be minimum or maximum. This Pm squared would be minimum of or maximum if ddx of Pm squared is 0. This Pm squared would be minimum or maximum if ddx of Pm squared would be 0. Then Pm squared, and therefore Pm would either be the shortest distance or the greatest distance. Yes or no? Right? Which means now, derivative of this with respect to x, 2 into x minus x1 plus 2 into y minus y1 dy dx is 0. Yes or no? Right? Right? Now if I divide, this 2 obviously gets cancelled. If I divide by x minus x1, then I get y minus y1 by x minus x1 into dy dx is 0, is minus 1. Yes or no? Yes. Now, y minus y1 by x minus x1 is the slope of this line m1, line joining p and m. Y minus y1 by x minus x1 is the slope of the line joining m and p. Dy dx is the slope of the tangent at m. Is the slope of the tangent at m. Call it m2. Yes or no? Dy dx is the slope of the tangent. And don't I get m1 m2 equal to minus 1? Don't I get m1 m2 equal to minus 1? That means Pm is along the normal to the curve. That means the shortest distance of P or the greatest distance of P from the curve will always be along the normal to the curve. Will always be along the normal to the curve. Yes or no? The shortest or the greatest distance of a point P from the curve is always going to be along the normal to the curve. Yes or no? Right? Now, this is absolutely cardinal, and you will save yourself a lot of effort if you take cognizance of this fact. And why this? I mean, you knew all along, let's say shortest distance of a point from a line is the perpendicular distance, which is normal to the line. Now in general for any curve. Right? Right? Now, once having a, can I remove the clutter from here? Have you registered the idea? The shortest or the greatest distance of a point from a curve will always be along the normal to the curve from the point P. From the point P, this then becomes a normal because this is a tangent and they are perpendicular to each other. Yes or no? I'll wipe this off. Now, having said this, we are done. See, the shortest or the greatest distance of any point P from this curve should be along a normal. Now from P, at Q, from symmetry you can see this must be the tangent. PQ therefore must be the normal. So therefore PQ will be the shortest or the greatest distance. No, it can't be the shortest. It has to be the greatest because shortest will be 0, P itself, isn't it? So PQ must be the greatest distance of P from any point on the curve. So the required point is Q 0, 2. You can select various points on the curve Q, but the greatest distance is going to be PQ. The greatest distance, because this is a normal, isn't it? The minor axis is a normal. Minor axis is a normal. Yes or no? Do you all understand this? Clear? So 0, 2. Problem number 12 of the sheet. There is a curve x squared plus 2y squared equal to 6. We want to find a point on the curve whose distance from the line x plus y equal to 7 is minimum. So we want to find a certain point on the curve whose perpendicular distance from this line is the smallest it could be, right? Now, this curve, as you can see, is an ellipse. X square by 6 plus y square by 3 equal to 1. X square by 6 plus y square by 3 equal to 1, right? This is a line y equal to minus x plus 7, right? In this case, a squared is 6, b squared is 3, and c for the line is 7, right? What is c squared? C squared is 49. right? C squared is 49 for the line. A squared m squared plus b squared. What is m of the line? M is minus 1. So a square m square plus b squared is like 6 plus 3, which is 9. So which means c squared is greater than a squared m squared plus b squared. That means if c squared were to be equal to a squared m squared plus b squared, this line would have been a tangent. If c square is less than a square m square plus b square, the line would intersect the curve at two distinct points. But if c squared is greater than a square m square plus b squared, this line must be like this, not intersecting the curve at real points. This must be the line. X plus y equal to 7 must be the line, not intersecting the curve at real points. Because c squared is greater than a square m square plus b squared, line would not intersect the curve at real points. Now, again, from the principle that we just learned, we want to find the shortest distance between the line and the curve. The shortest distance between the line and the curve, what I do is, if there is a certain point on the curve, then the shortest and the greatest distance would lie along a normal to the curve, would lie along the normal to the curve. Again, you know, if this is the tangent, this is the common normal, then this tangent must be parallel to this tangent must be parallel to this, right? And this will be the point of tangency. Then this would be the shortest distance. That means if this is a normal, a line perpendicular to the line x plus y equal to 7 and a line which is a normal to the curve at P, then along this would be the required shortest distance. This would be the required shortest distance. Now, this tangent in which case should be parallel to this line, because this line is perpendicular to both. So this must be like x plus y equal to some constant lambda, must be the equation of this tangent. I don't know. Let's figure out. How would I know? So we'll figure out. So you're right. If y equal to minus x plus lambda. So minus x plus lambda is a tangent. Y equal to minus x plus lambda is a tangent. The c squared, which is lambda squared, must be a squared m squared plus b squared for this to be a tangent. The c squared, which is a squared m squared plus b squared, for this line to be a tangent. Yes or no? Which is like a square m square plus b square. M is again, you know, as you can see, minus 1. A squared is 6. So this turns out to be 9. Lambda squared is 9. Right? So lambda could be plus minus 3. Would you want to believe that this must be x plus y equal to plus 3 and not minus 3? Think about it. This line, according to the equation, could have been x plus y equal to plus 3 as well as x plus y equal to minus 3, right? But I claim that this line is x plus y equal to plus 3 and not minus 3. This is x plus y equal to plus 3 and not minus 3. In fact, the important thing is x plus y equal to plus 3 is also a tangent, because lambda equal to plus 3 will give me a tangent. X plus y equal to minus 3 will also be a tangent. Please listen to me carefully now. Please listen to me carefully. These are parallel tangents. These are parallel tangents to the ellipse. How does one get parallel tangents? Let me make a mention. X plus y equal to plus 3 and x plus y equal to minus 3. Both are tangents. How do you get parallel tangents? You know, if O is the center of the ellipse and if this is a diameter, then tangents drawn at the extremity of a diameter will be parallel. In an ellipse, the tangents drawn at the extremities of a diameter will be parallel. That means this must be, say, x plus y equal to plus 3. This will be x plus y equal to minus 3. That means the two tangents are tangents drawn at the extremities of a diameter of that ellipse. Yes or no? Now, so this would be O. This would be a tangent drawn at P. This would be a tangent drawn at Q. This would be the tangent x plus y equal to 3, and this would be a tangent x plus y equal to minus 3. And this would be perpendicular to this line. This will be perpendicular to this line. Very clearly, x plus this q will give the farthest distance, and this will give the shortest distance, right? So x plus y equal to 3 will give me the shortest distance, right? So which means this is the tangent which will give me the shortest distance, which will give me a point P which is closest to this line. Are you lost? No. First of all, let me find this distance D, which is the distance between these two parallel lines. Distance between the two parallel lines is given by magnitude of C1 minus C2 by root 1 plus m squared, root a squared plus b squared. That means 7 minus 3, 4 divided by root 2 is the shortest distance between the two lines. Yeah, this all because P and Q are ends of a diameter passing through O. Also the normal at P. This is also normal at P. Not always. In this case, for shortest distance it does. Not all cases. Not all cases. Now, which means I need to find the point of tangency of x plus y equal to 3. I need to find the point of tangency of the line x plus y equal to 3. Suppose the point of tangency is x1, y1. Suppose the point of tangency is x1, y1. Right? I know the D now. 4 by root 2. Distance between these two parallel lines. 7 minus 3, 4 divided by root a square plus b squared. Right? Now I need to find the point P which is x1, y1. Hey, this tangent has an equation xx1 by 6 plus yy1 by 3 equal to 1 is the equation of the tangent at x1, y1. xx1 by 6 plus yy1 by 3. It can also be written as x by 3 plus y by 3 equal to 1. The same tangent could also be written as x by 3 plus y by 3 equal to 1. And these two represent the same line. One coefficient is equal means other coefficients must also be equal. That means x1 by 6 must be 1 by 3. That gives me x1 equal to 2. And similarly y1 by 3 must be equal to 1 by 3 or y1 equal to 1. That means this point P is 2, 1. Prove that in an ellipse, this is an ellipse, the perpendicular from a focus upon any tangent, suppose this is a tangent, and the line joining the center of the ellipse to the point of contact. Let me do it because I've taken this focus. Let me draw the tangent the other way. That will be better. This is the center C. This is the focus S, right? This is the point of tangency. This is the point of tangency. we want to show that the perpendicular from a focus upon any tangent and the line joining the center of the ellipse to the point of contact meet on the corresponding directrix. This is line joining the center to the point of tangency, and the perpendicular from the focus onto this tangent at P they meet at a point Q. We want to show that this point Q lies on the directrix. We want to show that this point Q lies on the directrix. In fact, what I do is a little bit of an engineering with the problem. First of all, let me refer to this ellipse as x square by a squared plus y square by b square equal to 1 is the ellipse. Let's say this point P has eccentric angle theta. Center is 0, 0. This point P has coordinates a cos theta, b sin theta are the coordinates of this point, right? Let me join CP. Let me say that the intersection of the directrix with CP is Q. Let's say this is the directrix, which is x equal to a by e. I'm doing a little bit of a tinkering with the problem. I'm tampering it a little bit. But there will be no loss of the fundamental issue by tampering. This is CP. And when produced, let's say it meets the directrix at Q. Let me find the coordinates of Q. Obviously, the x coordinate would be a by e, because Q is a certain point on the directrix. Q is a certain point on the directrix. CP produced will meet the directrix at Q. Now, what's the slope of PC? B sin theta by a cos theta, isn't it? Slope of PC is b sin theta minus 0 by a cos theta minus 0. Minus 0 by a cos theta minus 0, which is b by a tan theta, is the slope of PC. Slope of PC is b by a tan theta. Now this is a line passing through the origin with this slope. So equation of PC y equal to mx, line passing through the origin. No, see here. Y equal to mx, it's a line passing through the origin. So y equal to mx is y equal to b by a tan theta into x. Y equal to mx. Right? Now, how do I find q? Put x equal to a by e, you get the y coordinate of q, isn't it? Put x equal, for q, x is a by e, so I need to find y, isn't it? So for q, for the point q which lies on PC, x is a by e, y then would be b by a tan theta into a by e, which is b by e tan theta, so q has coordinates, b by e tan theta is the y coordinate. Yes or no? No confusion, right? Now, S is the focus, AE0. S is the focus, AE0. It would suffice to show that SQ is perpendicular to the tangent. If I can show that SQ is perpendicular to the tangent, then the problem is solved, right? Now what's the equation of the tangent at theta? X by a cos theta plus y by b sin theta equal to 1 is the equation of the tangent, right? X by a cos theta. What's the slope of the tangent? What's the slope of the tangent? Minus a by b cot theta is the slope of the tangent, yes or no? Minus a by b cot theta is the slope of the tangent, as you can see. B by a, sorry. b by a cot theta, minus b by a cot theta. Minus b by a cot theta is the slope of the tangent. Yes or no? Tell me. Now, if I can show that the slope of SQ into slope of the tangent is minus 1, then the problem is solved. Then this must be perpendicular at this point, right? Now, what is slope of SQ? y2 minus y1 by x2 minus x1, right? b by e tan theta minus 0 divided by a by e minus ae, right? Which is b tan theta divided by a into 1 minus e square, isn't it? E going here, a into 1 minus e squared is what transpires here. But 1 minus e squared is b square by a square. 1 minus e squared is b square by a square. So this 1 minus e square I replace by b square by a square. B squared by a squared. Yes or no? I'll repeat. What is this? This is b tan theta divided by e going here, a into 1 minus e squared. But 1 minus e squared is b square by a square. So it's b square by a square, right? This will get cancelled. This will get cancelled, which is a by b tan theta, which is a by b tan theta. So which means slope of SQ is a by b tan theta, a by b tan theta, and slope of the tangent is minus b by a cot theta. Product of the slopes is minus 1. Therefore, SQ must be perpendicular to the tangent. SQ must be perpendicular to the tangent, right? Of the sheet, which is problem number 14. Which is problem number 14. C1 and C2 be two circles, C2 lying inside C1. Circle C1, right? And C2 inside, and let's say the center of C1 is O1, say. Okay, center of C1 is O1. And then there is another circle C2 which lies wholly inside C1. C2 which lies wholly inside C1. These are two fixed circles, and let's say the center of this is O2. Say the radius of this is R1, the radius of this is say R2. Okay, they have radii R1 and R2. These are two fixed circles, centers O1 and O2, radii R1 and R2. Now there is a moving circle, a variable circle C, which touches C1 internally, and C2 externally, right? There is a circle C which is something like this, with center O, it touches C1 internally and C2 externally. C1 internally and many such circles can be drawn, right? Every time you draw one such circle, the point O, the center of the circle, will move. O is a moving point, the center of this variable circle C. And let's say the radius of this circle is R. Radius of this variable circle is R. We want to find the locus of O. We want to be able to find the locus of O. Now, What is OO1? Distance between these two centers. R1 minus R. This whole is R1. Minus R is OO1. Yes or no? Distance between these two centers is R1 minus R. Yes or no? No? OO1 is R1 minus R. OO2. OO2 is what? OO2 is what? R plus R2. OO2 is, this is R, this is R2. R plus R2. OO2 is R plus R2, isn't it? OO2 is R plus R2. Line joining the centers of the two circles. Distance between them is going to be R plus R2. Yes or no? Ayush, where are you lost? OO2 is R plus R2. Right? Add these two. OO1 plus OO2 is R1 plus R2, which is a constant. R1 plus R2 isn't it a constant? R1 plus R2, radii of the two fixed circles, is a constant. O is a moving point. O1 and O2 are two fixed points. O moves in a manner that sum of its distances from two fixed points, OO1 and OO2, is a constant. Locus of O must be an ellipse with foci O1 and O2. The locus of O must be an ellipse with foci O1 and O2. Yes or no? O describes an ellipse whose foci are O1 and O2. Because OO1 plus OO2 is maintained constant. Yes or no? Right?